So let's talk the nitty-gritty details about Sn1 reactions. Remember, Sn1 means substitution, nucleophilic, unimolecular. Okay, here's my substrate. Here's my nucleophile. It makes these products. Guess that those are the products formed, but how do those products form? We care about the mechanism. So we've already said previously that an Sn1 goes through a carbocation, a familiar intermediate. That's great. Excellent. How does it work? Well, the bromine is my leaving group. The bromine acts like a diva. There is nothing that instigates it. The bromine just leaves, up and leaves. And when the bromine with it, it leaves behind a carbocation. Bromine left, took his electrons, gone. See ya. Leaves behind a carbocation. Carbocation can then be attacked by our nucleophile, and this time our nucleophile is water. Water is our solvent, but also our nucleophile. When something is a solvent that is also a nucleophile, like this, we call that solvolysis. The solvent getting involved, solvolysis. Specifically when it's water, it's called hydrolysis. So water is the solvent and it's getting involved in the reaction, hydrolysis. This is a solvolysis reaction. Sn1 is often called solvolysis. Okay. So water attacks the carbocation, leaves me this intermediate, and then water comes to clean up the mess, just like it did before. It's nice that this step, something we've totally seen before, this step, something we've totally seen before, this kind of product, something we've totally seen before. The only thing that's new is that how this reaction started. We started with an alkyl halide, not an alkene. So diva leaves to start this mechanism. Alkene attacks the hydrogen of the acid in an addition reaction. So from the carbocation forward, it's a lot the same, but making the carbocation is slightly different. We said this stands for substitution. Molecular. Unimolecular means there's one thing involved in the rate law, one thing in the rate determining step. So this reaction is 1, 2, 3 steps. Which of these steps is the rate determining step? Obviously, it's the first one, because any reaction in the rate determining step is the step that forms the carbocation. So this first one is my rate determining step. So that means my rate law would involve the reactant of my first step and only the reactant of my first step. So this is the specific rate law for this reaction, but the rate law for an Sn1 in general is dependent on the substrate and the substrate only. The nucleophile, the base, the solvent, all that stuff is of an Sn1. Okay. If we draw a reaction coordinate diagram of that reaction we just drew, reaction progress, energy, we have a shelf that had my alkyl halide on it. We have a high shelf that has my carbocation on it. We have a much lower shelf that has my intermediate that has the protonated alcohol. And if it's exergonic overall, way down here is my alcohol. I'm going to have 3 humps that connect these things together. 3 humps. Which hump is the mandatory? The first hump is taller than all of the other humps. The reason being that first step is your rate determining step, and the tallest hill is your rate determining step. Yeah? We have 3 different transition states. We could draw them if requested to do so, but we haven't been requested to do so, so let's not. The activation energy for the overall reaction is the highest one. That's this to the rate determining step. That's EA for the first step, which is really kind of the activation energy overall. Individual activation energies, EA1, EA2, EA3. Yeah, we can also talk about the delta G of the overall. We've drawn enough reaction coordinate diagrams that you kind of know the plot now, right? Yeah. Every single intermediate has its own shelf. The starting material and reactants have their own, the starting material and products have their own shelves. Yeah. Everything's connected by a hump. You got to know the rate determining step to know which hump is the highest. Okay. There are several factors that influence the rate of Sn1 reactions. Does this list look familiar? It's the same kind of list that the previous Sn2 had. If we don't go through all the specifics, but highlight a few things, because we're making carbocations, we actually want crowded substrates. No social distancing in Sn1 reactions. We want the crowd. Bring on to make that carbocation as stable as it possibly can be. The nature of the leaving group. Well, weaker bases make better leaving groups. We said before that statement we made for Sn2 was universal. Weaker bases make better leaving groups. The nucleophile for these, neutral, is often what it is as opposed to anionic. And furthermore, it's often the solvent in Sn1 reactions. Yeah? It's a weaker nucleophile. Weaker nucleophiles are generally better for and protic solvents, protics, are generally faster than aprotic solvents. Yeah? Kind of the same as Sn2, but equally opposite, right? Yeah, maybe. All right, carbocation formations, rate determining steps, kind of what we just said. More stable carbocation means faster first step, means faster Sn1 overall. So that makes tertiary better than secondary, better than primary, better than methyl, because it's about carbocation stability. That means a tertiary alkyl halide reacts faster in an Sn1 than a secondary alkyl halide does in an Sn1. In fact, let me just do this right here. We're not going to make any methyl carbocations. We might see primary, but it's really pretty rare. Allylic and benzylic are very stable carbocations because they have, what is it that they have? Resonance. In fact, an allylic carbocation that's primary is even more stable than a tertiary carbocation. Yeah? An allylic carbocation that is primary is even more stable than a tertiary carbocation. Resonance is a big factor. Remember, this is stabilized by hyperconjugation. This is stabilized by a little bit of hyperconjugation and resonance. And resonance is a more important factor, a better stabilizing factor than hyperconjugation. So, if allylic and primary is more stable than tertiary, I bet benzylic and primary is even more stable than that. Yeah? So the last example of Sn2, we said allylic and benzylic were good as long as they're not tertiary. We don't have to make that statement here. Primary does not make great carbocations on its own, but when you have the stability of resonance, primary carbocations are really pretty fabulous. Aryl and vinyl, they don't do none of this. They don't do Sn2, they don't do Sn1, they don't do none of this. The name of the game with carbocations is more crowded, more better, generally. Resonance plays a different factor. Okay, that was a substrate. How about the nucleophile? The nucleophile is not involved in the rate law. The nucleophile is not involved in the rate determining step. So if you increase the concentration of the nucleophile, it does not have any effect on the rate whatsoever. No effect. Only the substrate affects the rate. So if you dump a bunch of water into that first reaction we talked about, the reaction does not speed up whatsoever. If it were going via Sn2 mechanism, it's not. But if it were, it would go faster when you dump a bunch of water. This one's not. Carbocation must form in the rate determining step. This is an old wisdom from my professor. There are 5 times that a carbocation can form in the presence of a strong base. You ready? Never, 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 never. Never, 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 never. There are 5 times that a carbocation can form in the presence of a strong base. Never, 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 never. What does that mean? Let me translate that little saying into something useful. If I have this substrate that I had previously and hydroxide, de-believes is how that mechanism wants to start. But what this is saying is that this is considered a strong base. This is a very strong Lewis acid, super strong electrophile. These things cannot coexist in solution, as in this thing will never, ever, ever form when you have a strong base around. So, if you have a strong base, you must do substitution by Sn2, if at all. So if I go back and look at this is a tertiary alkyl halide. Can I do Sn2? No. I have a strong base. Can I do Sn1? No. So this reaction actually should lead to no substitution product. No substitution product on this blue reaction I've given down here. Ain't happening. Strong base, not Sn1. Tertiary alkyl halide, not Sn2. That's all I got. All right, the solvent. How does the solvent affect an Sn1? So first of all, in general, we're talking about polar solvents when we're talking about these kinds of things. But let's compare a couple of solvents. If I have a cation in the presence of water, that cation can be solvated like so, where I've got little dash, dash, dash bonds between the cation and the oxygen. Why did I point the oxygen that direction? Because the oxygen is partially negative due to it being more electronegative than hydrogen. We've got a dipole pointed that direction. Yeah, hopefully that's kind of old news. If I have something like DMSO, DMSO can do the same dang thing. That oxygen in DMSO is partially negative, so that partial negative in DMSO can also solvate my cations. So according to this picture, there's no difference in solvation of cations, whether your solvent is parodic or aprotic. It's true. But solvation of anions is different if you're in protic or aprotic. Give me another slide. Hold on. If you're in aprotic solvents, that anion is not so easy to solvate. Let me show you. A little DMSO, it's the sulfur that has the partial positive charge, and that partial positive charge is kind of buried. It's tucked beneath the other atoms. It's buried is really the only easy way to say. You cannot really make a good dot, dot, dot bond. I showed one anyway, but you cannot really make a good dot, dot, dot bond between a minus charge and a positive, partial positive in an aprotic solvent, but you can do that in protic solvents because they all have hydrogen bonding ability. Remember, that's what separates protic from aprotic. Hydrogen bonding ability, yeah. So cations are solvated the same regardless of the solvent. Anions are solvated better in protic solvents. Okay. How does that wrap in with what we talked about the last time? Anions are our nucleophiles in these substitution reactions a lot of times. Not always, but anions are our nucleophiles. If that nucleophile is collected with a bunch of, is weighed down with a bunch of solvent molecules, it's not as available to attack things. So really what I'm explaining so far is anions are considered naked, for real. Anions are considered naked in aprotic solvents. So that's really the reason why SN2 reactions are faster in aprotic solvents, because Sn2 generally uses anions as nucleophiles. But in Sn1 reactions, we don't usually have anionic nucleophiles. We usually have neutral nucleophiles. So the solvation of the anions doesn't matter so much. The cation is solvated, the carbocation is solvated regardless of the solvent type. But protic is generally favored in Sn1, often because the solvent itself is the nucleophile. I realize all that solvent stuff can be kind of confusing. Remember, the solvent is the lowest on the totem pole of things we consider, so don't really worry too much about the solvent effects of these things. We will talk about it more as we get our feet under us a little better. All right, let's walk through an example. Here is an alkyl halide substrate. It's a secondary alkyl halide substrate. This thing that must be my nucleophile doesn't have a charge that I see, so it's a neutral nucleophile. And there is not a solvent listed. In fact, it's most likely that this thing is also the solvent in the reaction. We're going to say it's protic, because it is. That OH right there is protic, yeah? So, putting this evidence together, secondary alkyl halide, neutral nucleophile, protic solvent, Sn1. I realize our title says we're going to do Sn1. Let's do Sn1. We will start to collect our data. This is Sn1. The way it starts, Diva leaves. Bromine, nothing instigates it. It just packed up and left. Diva leaves and leaves behind a carbocation. There's a beware up here, but I'm going to tell you to beware in the other direction from what your brain is probably thinking right now. When you create a carbocation, students often start seeing shift, I should shift happens, shift. Yeah, a shift does happen, but this carbocation, this current carbocation, exists as well and can be attacked by a nucleophile as well, will be attacked by a nucleophile as well. So don't forget to attack the current carbocation. Don't just shift and make that as the only product. The current carbocation should also be shifted. No, attacked. The current carbocation should also be attacked. O attacks makes an OH+. It's the O with the H. One day, when you're a little bit further along in your organic journey, we will explain which O it should be that attacks. It should be the other O, but I don't know if I want to go through all the details of why right now. But O attacks, O cleans up, we end up with a neutral ester product. Should I, shouldn't I? Should I, shouldn't I? As in so many things in organic, it's really all about resonance. I can dump in electrons, dump up electrons like that. I get this as the resonance picture after those two arrows I just drew. So which of these oxygens, top oxygen or OH oxygen, has greater electron density? The top oxygen has much greater electron density than the OH oxygen because of this resonance picture. This resonance picture said that oxygen even has a full formal negative in one of the resonance pictures. So the hybrid definitely has some negative characteristics of there. The OH carbon, the OH oxygen, has a partial positive in the hybrid because in one of the resonance structures it's got a full legit positive. So really, when I draw this OH attacking that carbocation, that's incorrect. It should be the top oxygen attacking because it has more electron density. Then when I cleaned up, I did use the proper oxygen to clean up because that oxygen has more electron density. What I'm saying as a take-home message is this oxygen is more basic, has a lone pair that's more focused. This oxygen is less basic because of resonance. So what does that do for me in my mechanism up there? Well, I get to the same product either way. Let me show you. If I draw it in orange, I'm going to attack my carbocation with my top oxygen this time. I get this O with a plus, and then my acetic acid comes to clean up again. Cleans up the H out there. Well, the deal with cleaning up the H out there, oh, it's getting a little squishy. We're going to have to erase them. The deal with cleaning up the H out there is you end up with this bottom product. But that's not the most stable version of this bottom product. The most stable version is this. It's the exact same product that I just drew over here. Aren't you so glad I explained all this orange stuff down here? Yeah, all the orange stuff is not necessary. You can use, in my opinion, you can use this OH to attack and use that same thing to clean up, it's fine. Or you can use this O to attack and clean up with that same O, it doesn't matter. I do want you to know that the top oxygen has more electron density and is a better base and therefore a better nucleophile than the bottom one. But you don't have to draw it the fancy orange way that shows resonance for me. It's the right way, but you don't have to show all the fancy stuff for me. Okay. So we got this purple product that we also drew an orange product getting the same thing. But that carbocation could also undergo a rearrangement. What kind of rearrangement? It could undergo a methyl shift. The methyl is moving with its electrons. Take note of where the butt of my arrow is. The butt is coming from the electrons holding the methyl onto that carbon. I get that blue carbocation that's now tertiary and more stable. And I'm going to draw the mechanism the right way this time just because I'm a real organic chemist and it hurts me when I do it wrong, even though it's simpler for you guys to understand. Yeah. And then I'm going to clean up. Everybody clean up. Clean up this guy. And I'm going to go ahead and draw my resonance arrows to get me to my more stable winner chicken dinner resonance picture. There is my product. Isn't it great? This reaction creates two constitutional isomers. What about stereochemistry? Should we include stereochemistry? Is this carbon an asymmetric carbon? Yep. And did that carbon used to be a carbocation? Yep. That's trigonal planar? Yep. And when that acetic acid attacks, could it attack from the top and the bottom? Yep. So what that really means is I get a wedge and I get a dash on my ester. So two constitutional isomers were created, the purple and the blue. But that purple is really two different stereoisomers that are enantiomers. And if I revisit my blue down here, is that an asymmetric carbon? Nope. Is that an asymmetric carbon? Nope. So since both of those are not asymmetric carbons, that's done. I made three total products, two constitutional isomers, two stereoisomers, three total products in this reaction. Phew. That was so fun. How about some more? Okay. I've got a secondary alkyl halide. This is the only thing I see, and it's neutral. It's also a protic thing. Yeah, it must mean that my solvent is going to act as my nucleophile. Yeah. I'm going to do Sn1. Deleaves and leaves behind a carbocation. That carbocation can be attacked by my nucleophile. It's ethanol this time. Ethanol attacks and brings the hydrogen and the two carbons along for the ride. And another ethanol comes to clean up. Clean up, clean up. Everybody clean up. There's my ether product. Isn't it fabulous? But beware. Oh, what am I bewaring of? Beware. Carbocations are involved. That carbocation can undergo a hydride shift. That carbocation could also undergo a ring shift. Oh, yeah. We're going to do a hydride shift to make this blue carbocation. And then ethanol attacks that blue carbocation. Getting a little squashy. Ethanol cleans up. Oh, carbocations everywhere. And I get that blue product that we wound back on itself over there. I'm going to use that ring shift to make a purple product. Do you have to draw the ring shift in this orientation? No, but I think it's helpful to see why carbon number 3 is the carbon that has the positive. Ethanol attacks carbon number 3 carbocation. Ethanol brought both carbons and the hydrogen. Ethanol, clean up, everybody clean up. Done. 3 constitutional isomers. The purple, the green, and the blue. 3 constitutional isomers. Oh my. What question comes next? Tell me about the stereoisomers. Ooh. If I start with my blue, just because it's kind of at the top-ish, that carbon, is it asymmetric? Nope. Are any carbons in that blue thing asymmetric? Nope. So blue is an achiral molecule because it has no asymmetric carbons. What about green? Does green have any asymmetric carbons? Yes. It has 1 asymmetric carbon. It's that one. Did that carbon used to be a carbocation? Yeah, it did used to be a carbocation. What that means is I have a dash and a wedge. I tried to color on top and that did not work. A dash and a wedge on that. Whew, it's crowded, so crowded. A dash and a wedge on that oxygen, like those 2 orange products. Note, I think I might trust you enough now for you to use something called a squiggle. What? A squiggle. That is officially a squiggle on my green carbon right there. A squiggle. What is a squiggle? A squiggle represents both dash and wedge. So that green molecule that has a squiggle on it, what that's telling the reader, the onlooker, is that both dash and wedge version of that oxygen exists. That green thing with a squiggle represents 2 compounds, the 2 orange compounds. Okay. In this bottom purple one, do I have any asymmetric carbons? I do. This one and that one. That's carbon 2 and carbon 3, according to my numbers from previous. Did carbon 3 used to have been a carbocation? Yeah. What that means is carbon 3 should be racemized, should be dashed and wedged. We can give carbon 3, you guessed it, a squiggle. That's not a dash, it's not a wedge, it's a squiggle. They are different. Boy, aren't organic chemists crazy? Carbon number 2 has a methyl hanging off of it. Did carbon number 2 used to be a carbocation? Yeah, carbon number 2 used to be a carbocation. What that means is carbon 2 should be racemized. Carbon 2 can be represented as a squiggle as well. So those 2 purple squiggles mean similar but different things than the green squiggles. Those 2 purple squiggles are on different carbons. What that means is those 2 purple squiggles represent all 4 stereoisomers of that molecule are in existence. What for? I guess we'll make them red. We got a whole rainbow over here. Wedge oxygen. Wedge methyl. Dashed oxygen. Dashed methyl. Wedged oxygen with dashed methyl. And the opposite. Dashed oxygen with wedged methyl. It's much easier to slap 2 purple squiggles on there, isn't it, than draw 4 of those? Yeah. Structured drawing programs online don't usually allow you to draw squiggles, which I appreciate. It means you have to fully understand what squiggles mean. So I will allow you to use squiggles when you're drawing things for me that I will grade by hand, but you must use your squiggles responsibly. Don't put squiggles all over everything because sometimes squiggles are wrong. Okay. Predict the products of the following Sn1 reactions. First, our analysis. I have a secondary alkyl halide. I have, I don't know who's my nucleophile, but both of those things are neutral. And one of those things is protic, so it must mean I've got a protic solvent. Okay, so the real question is, I'm going to do Sn1, sorry. The real question is, who's my nucleophile? Oh, brother. Nitrogen versus oxygen. Who's my nucleophile? I have this mantra, better base, better nucleophile. Better base, better nucleophile. Except you have to be careful when your solvent is protic. Ooh, check. We got a protic solvent. Your solvent is protic if your nucleophilic atoms are largely different in size. Nitrogen versus oxygen, are they largely different in size? They're a little bit different because they're next door neighbors, but they're not vastly different. So this is not about size. Better base, better nucleophile, period. Even though the solvent is protic, the 2 atoms under consideration have similar radii, so it's about better base, better nucleophile. Okay, so we got to be able to detect who's the better base, because I don't love acids and bases. I'm still real bad at them. I don't get it. It's about electronegativity when you're considering nitrogen and oxygen and other things that are next door neighbors on the periodic table. Nitrogen versus oxygen. Oxygen is more electronegative. That means oxygen is going to be a better acid. That means oxygen is going to be a worse base. Yeah? So the stronger base is the less electronegative atom. Better base, better nucleophile. I have found my nucleophile, and it's NH3. All right? So much analysis. Now it's finally time for a mechanism. Debelieves and leaves behind a carbocation. I'm going to just stick that methyl over there. We'll analyze his stereochemistry in a moment. Debelieves leaves behind a carbocation. Nucleophile that I finally detected is my nucleophile. Attacks, said carbocation. Like so. And something comes to clean up the mess because that nitrogen is positive. It's probably going to be the thing that's the better base, wouldn't you agree? Because we're cleaning up a hydrogen. Yeah. I get this blue product, which is an amine. Yeah. Okay. Is that all? No, that's not all. Sn1 reactions involve carbocations, and carbocations often rearrange if you can make a more stable carbocation. What kind of shifty shifts can that carbocation do? You can do a little hydride shift. Hydride shift to make this green carbocation. Nitrogen attacks just like before. Nitrogen cleans up just like the blue route. And we home free. Eventually, when my hand catches up with my mouth. I got green product, I got blue product. You should tell me about the stereochemistry. You should know about the stereochemistry of those products. Fine, I'll do it. I know you want me to. Fine. All right. This methyl was wedged. Did anything happen right here to that methyl? Nope. That methyl should stay wedged. No, he's dashed. Sorry, I mixed up my words. That methyl was dashed in the beginning. He should stay dashed. Methyl should stay dashed because not a dang thing happened to that carbon in this whole blue process. Not a dang thing happened to that carbon. It's still asymmetric in the end, so leave him dashed. When that amine came in attacked, that nitrogen came in attacked, it attacked an sp2 trigonal planar carbocation, so it could attack from both sides. So maybe I can use my newfound freedom and put a squiggle on that nitrogen. That squiggle actually represents how many molecules? 2. It represents this and that. Oh, that's a 2, that's a 2. What's the relationship between these bottom two blue circled compounds? They are diastereomers. Sometimes students start associating squiggles with meaning enantiomers. Not necessarily. We had one stereocenter, one asymmetric carbon that was explicitly defined, and then another that was a squiggle. So this is a pair of diastereomers that is represented up there. Okay. Cool news about the green one. That is not an asymmetric carbon anymore, so no dashes, no wedges needed whatsoever. Yeah, that methyl started out dashed, but when he became a carbocation, it's going to get racemized, but then in the end it's not asymmetric, so forget that. All right, we are in the home stretch. Let's do another one. Analysis. I have a secondary alkyl halide. I have some stuff that's neutral, but I'm not really sure who's doing what. I have a thing that's protic. So, okay. I need to decide on who's my nucleophile. Better base, better nucleophile. Better base, better nucleophile. Better base, better nucleophile. Except when your nucleophilic atom is different and the atoms are vastly different atomic radii. O versus S. Are those vastly different atomic radiuses? Heck yeah, they are. S is in the third period while oxygen's in the second period. They are very different sizes. S is a much larger radius. So what that means is the bigger atom is the better nucleophile. When you're protic, when your solvent is protic, and your two atoms are vastly different radii, protic solvent, bigger atom, better nucleophile. So this is my actual nucleophile. The S is my actual nucleophile. All right, mechanism time. Dave leaves and leaves behind a carbocation. I know that the repetition gets a little bit exhausting sometimes, but I also hope that you will hear me repeating these things when you go to take your MCAT soon enough. Dave leaves and leaves behind a carbocation. Nucleophile attacks the carbocation. Why am I leaving that methyl wedged? Well, because it's the right thing to do, and I have bad habits, and I forgot to ask you about it. I just did it on my own. Whoops. Something comes to clean up. We'll make it the SH. No, we won't. The oxygen is a better base. Yeah, I know. Details. Yeah. The oxygen is a better base, even though it's a protic solvent. It's just nucleophilicity changes. I know. Don't hate me. Yeah. While we're here, we might as well talk about stereochemistry before we move along. That sulfur should be a squiggle. That should be the wedged version. Wow, that's real small. Oh, it's not an ethyl. It's just a methyl. Methyl. And the dashed version. But the methyl over there should stay as it was because no reaction happened at that thing. Those green molecules are diastereomers. All right. Is that all? No, of course. It's never the end. I've learned enough now. It is never the end. Yeah. Means you've been in the class long enough. That carbocation can undergo a shift, a rearrangement. What's happening? We're going to do a little hydride shift. Not only is the new carbocation tertiary when the first one was secondary, the new carbocation is benzylic, and benzylic is fabulous. So that sulfur attacks that benzylic carbocation. We get an S with an H and a methyl, and we're going to go all the way over there because what's the mechanism if it's not difficult to follow, right? All right, we got this thing. It's getting a little crooked. 1, 2, 3 carbons. We got an S with a methyl. We got a methyl. There's my product down in the corner. Yeah. If I put some stereochemistry on that thing, what kind of stereochemistry should I give? I give a squiggle to both the sulfur and the methyl. Why do I give it to both the sulfur and the methyl? Well, because that's a tetrahedral carbon, and I need to show the configuration of all 4 things around that carbon when all 4 things are explicit, meaning we always assume there are hydrogens in place when, there we go. We always assume there are hydrogens in place, like when something is wedged, we would know a hydrogen's on the dash on the same carbon. But no, all 4 things are explicitly drawn down here around this tetrahedral carbon, so we need to squiggle 2 of them because 2 of them need to be designated as in and out of the plane. Maybe that was clear, maybe that was not clear, I don't know. All right, that's the end of Sn1. Wasn't it fun? Here's a little summary. I don't think I need to read you these words, right? Yeah, it's basically what we've said over Sn1 and Sn2. All those words, a lot of words. There for your viewing pleasure. You should try these. We should probably talk about them as well, but you should try these on your own. Try to figure out if it's an Sn1 or an Sn2, because it might be either. Good luck. Peace out. See you when it's elimination time.